Greetings to you each. We're going to be starting a very important section today, relations and functions. We're going to talk first of all about relations, a general concept, then we're going to get very specific and talk about a specific kind of relation called a function. So let's talk about relations first of all. First of all, a relation is a very familiar concept. A relation is simply a relationship. Between the elements of two sets. Now, there are going to be a multiplicity of ways of demonstrating a relation. In fact, we're going to use 4, and I'm going to show you each of the 4 right now. The first is the most visual and I think the most telling, the most graphic. It's called a mapping. And it just shows how things in one set relate to things in a second set. For instance, let's say 1 is related to 1, 2 is related to 4, 3 to 9, and 4 to 16. Some of you can probably even tell what the relationship is. It's specific. I'm simply squaring the first element to get the second element. 1 squared is 1, 2 squared is 4, etc. But it doesn't matter. This is still just a relationship between elements in one set and elements in another. Now, once you have the two sets designated and you have a relationship between the two, a relation, the first and second set have names. The first set is called the domain. You've probably heard this before. And the second is the range. That's some familiar terminology. You got a mapping. It shows you the relationship between stuff in one set and another set. And the first set is called the domain, and the second is the range. First way to indicate a relation. Second way to indicate a relation is simply a group of ordered pairs. Now, if you'll notice, I have ordered pairs designated by this mapping. I can show the same relation, not with a mapping, but with ordered pairs. Watch this. 1 is related to 1. All right. 2 is related to 4, etc. 3 to 9, 4 to 16. Exactly the same relation, but in a different presentation. 1 is with a mapping, the second is with ordered pairs. Now, I can still talk about the domain and the range of this particular presentation of relation. The domain in this instance is simply the set of all first elements. Every ordered pair has a first and a second element. First and a second. So the set of all first elements is called the domain, and it's 1, 2, 3, and 4. One, 2, 3, and 4. Same domain, right? Just a different presentation of it. The range, likewise, is the set of all second elements. 1, 4, 9, and 16. So on Hawks, you will be given a group of ordered pairs and asked to recognize the domain and the range. No problem. The domain is simply all the first elements. The range is simply all the second elements. Not too tough. And we're going to go back to these illustrations and talk about them in terms of there being a function or not, but we'll get to that in just a second. All right, that's the first two ways to talk about or to represent a function. There's a third way, and that's with an equation. Here we go. Y equals 2x plus 3. That's an equation. And your relation and function equations are typically solved for y. And if they're not solved for y, you probably want to go ahead and solve them for y. Y equals is the typical way a relation or a function is represented. Now, once I have a function, we can talk about something called evaluating a function, and we will get to that in just a second, but I'm going to just leave it at this. An equation is another way to represent a function. I'm sorry, a relation. Now think about it. I can talk about ordered pairs with this guy, can't I? The first element in my ordered pairs is the x. All right, choose an x. Let's say we choose 0. 2 times 0 is 0, plus 3 is 3. Y equals 3. We've got an ordered pair. Pick another x. 1. 2 times 1 is 2, plus 3 is 5. The point 1, 5, or the ordered pair 1, 5, is part of this particular relation. So again, relationship between x's and y's. You pick the x and find the y, and you'll be able to recognize something about what this particular relation represents. We'll get back to this in just a second when we talk about function. Let's talk about the fourth way to talk about a relation, and that is with a graph. Let's say a graph of the relation y equals 2x plus 3. What does it look like? Well, I know something about it, right? This is in slope-intercept form. I know it's going to be a line. I know it has a y-intercept of 3. I know it goes through this point right there. 1, 2. I know it goes through that point right there. I know it's got a slope of 2, so it's a pretty steep slope. But I might be wise to find some ordered pairs, x's and y. Just what we did here. Pick an x, find a y. So I'm going to pick an x, 0. 2 times 0 is 0, plus 3 is 3. No surprise, that's our y-intercept. 1. 2 times 1 is 2, plus 3 is 5. The point 1, 5 is one of my points. 2 times 2 is 4, plus 3 is 7. 2, 5, 6, 7 is my point. I think I got a good picture of what my line looks like. Looks like this guy right here. Here's my line. Y equals 2x plus 3. So this is my third way to represent a relation. It again is made up of an infinite number of ordered pairs, an x and a y. The x's are related to the y's. Elements in one set are related to elements in another. All right. Now let's go back and get more specific and talk about a function. Because a function is a very specific kind of relation. A function is a relation, so it's a subset of relations, a relation in which no first element is repeated. No first element is repeated. All right, when I look at a mapping, let me see if a first element is repeated. Is there more than one line of relationship coming from one? Is one other than 1, 1? Is 1 related to some other number? No. Is there more than just one line of relationship from 2? Nope, just 1. How about from 3? Nope, just 1. How about from 4? Just one line of relationship. Since there is only one line of relationship coming from each of these first elements, no first element is repeated. This is a function. And in fact, when you're looking at a mapping, all you have to do is go like this. Look at the domain. Is every domain element related to just one thing in the range? Yep, just one line of relationship from each element in the domain. Hey, look at a weird mapping. Watch this guy. All these elements are related to 5. Question, is this a function? Is any first element repeated? Is a first element related to more than one second element? And remember what I said, just look at the first set, the domain. Does every first element just have one line of relationship? It does. This, ladies and gentlemen, is a function. It's a weird function, but it's a function. Watch this. One is related to 1, 1 is related to 2, 2 is related to 3, 2 is related to 4. Is this a function? Is every first element just related to one second element? No. Check out the first set. Is there only one line of relationship coming from each element? No. Here's a problem. Here's a problem. 2 lines of relationship. One is related to more than one thing in the range. So this is not a function. Check your elements in the first set. If there's only one line of relationship, it's a function. If there's more than one from one of the elements, just one of the elements, it's not a function. So that's how I determine if a mapping is or is not a function. All right, what if you don't have a mapping? What if you have ordered pairs? Again, I ask myself, is any first element repeated? Let's see, I got a 1, I got a 2, I got a 3, I got a 4. Hey, no repetition in the first elements. So this, likewise, is a function. What if I had ordered pairs like this? 1, 2, 2, 3, 3, 4, 3, 5. Does that represent a function? No, because there is a first element repeated. Look at your first elements. 1, 2, 3, 3. First element repeated, not a function. So that's all you have to do. All you have to check is the first elements to see if any first element is repeated. Hey, this is a relation, but it's not a function. So I got ways to check to see if a mapping is a function. Check the domain. Every element just have one line of relation. Yep, it's a function. Ordered pairs, check your first elements. Any first element repeated? No, then it's a function. All right. Let's go to an equation. Now, one thing you're going to notice about an equation that is a function is that another way, in fact, a more familiar way in which functions are expressed is not as y equals something, but as f of x equals something. This is called function notation. Hey, it's talking about the same relationship, the same set of ordered pairs. It's just the second one uses something called function notation. F of x. F of x, g of x, h of x. You can use a variety of letters, but it simply says we got ourselves a function. And once you got a function designated, a function is basically a black box. It's this magic box that takes elements into it and spits out something else. You put a number in it, it spits out another number. Put a number in it, it spits out a number. And this tells you how it spits out the number. All this function does, 24/7, 365 days a year, even in leap year, is you give it a number, it multiplies it by 2 and adds 3. That's all this function does. So if I give this function the number 5, that's my input. This function says, oh, you give me 5, 2 times 5 is 10, 10 plus 3 is, it spits out 13. I put in 5, it spits out 13. I put in 7, 2 times 7 is 14 plus 3 is 17. I put in 4. The function says 2 times 4 is 8 plus 3 is 11. I put in -2. The function says 2 times -2 is -4 plus 3 is -1. So a function is simply a mechanism that translates one number into another. You put a number in, you get a number out. Input, output. No surprise, this is your domain, this is your range. These are the numbers that you put into the function, these are the numbers that it spits out. So I can express this same idea with ordered pairs. Watch this, 5, 13. 7, 17. 4, 11. -2, -1. Right? Same relationship, same concept. I put a number in, it spits a number out. I put this in, it spits this out. All right. Hey, I can talk about something else once I have a function notation. Once I know, for instance, that f of x is 2x plus 3, here's something that Hawks is going to ask you. It's going to say, okay, what is f of 5? That means exactly what we did here. It means everywhere you have an x in your function, you put a 5. F of x is 2x plus 3. F of 5 is 2 times 5 plus 3. 10 plus 3 is 13. No surprise. So this is another way of saying I got an input and an output. What's f of 10? Well, let's find out. It means 2 times 10 plus 3. So whatever the value you're asked about, substitute that everywhere for x. That's 20 plus 3, 23. Hey, I can be more general. What's f of a? I don't know, it's 2 times a plus 3. And that's all I can write, right? 2a plus 3. And again, these are ordered pairs. 5, 13, 10, 23, a, 2a plus 3. Those are all ordered pairs that talk about this particular function, f of x equals 2x plus 3. All right, let's consider the graph. Let's consider this function f of x equals 2x plus 3. Now, some of you guys know the answer to this question. Does this line that we just drew it here, we found some ordered pairs and drew the line, does this line describe a function? Do you know a test that I can apply to a graph and determine if the thing is a function or not? Some of you do. It's called the vertical line test. And there's a variety of ways you can phrase this, but a good way to say it is a graph is not a function if any vertical line, that's any in the universe, any you can imagine, any vertical line cuts the graph, intersects the graph more than once. Again, all these notes will be posted on your Quickly content, so you don't need to copy this stuff down. But there's a vertical line test. Now, I got to use my imagination on this because I cannot draw every possible vertical line. But as I imagine any vertical line, it is cutting the graph in only one place, right? Hit it. Got it. Got it. So every vertical line I draw intersects the graph in only one place. This guy passes the vertical line test. It is therefore a function. Now you can apply the vertical line test to any single graph you want to. Check this guy out. Let's do the graph of a circle. Does the circle describe a function? Hey, there's a vertical line. It doesn't cut it in more than one place. That one doesn't cut it in more than one place. That one doesn't cut it. That one doesn't cut it. I can draw an infinite number of lines that don't cut it, but there's one at least that cuts it in more than one place. Here's another one. It cuts it in more than one place. This guy we say fails. Hate to use that word in a math class, but it fails the vertical line test. So therefore, not a function. In fact, no circle is going to be a function because there are vertical lines that cut it in more than one place. All right, try a parabola. Upward turning parabola. Is that going to describe a function? Absolutely is. Because every vertical line cuts it in only one place. Function, yep. This guy passes the vertical line test. So if I have a graph, I can see if it passes the vertical line test to determine if the thing is a function or not. All right. Let's look at a couple of your problems. By the way, I'm going to put the entire problem set on Quickly content, but I'm going to look at a couple of the problems now just to see if something rings a bell as far as important concept. Here's an important concept. Let's look at one thing we didn't answer is if I have a function, that function we already looked at, and I have it in equation form, is this a function? Now I know it is already because I went ahead and graphed it, and it represents a function because it passes the vertical line test. But what if I didn't have a graph of this thing? What if I didn't know what it looked like? Is it a function or not? When I have an equation and I want to tell if it is a function or not, there are very specific guidelines. And here's what those guidelines are. Now this is, I'm going to put this, one of these clean sheets on your Quickly content notes, and I would highly encourage you to run this off and have this handy. Keep this one sheet. It's a very valuable expression of two concepts. All right, first of all, is this guy a function? My first inclination is to say, yes, it's a function. And here's why I would say it's a function. Because the domain can be anything. Can you pick any x for this particular function? Any x at all? Yeah. And will you get only one y? Whatever x I pick, will you get more than one y? Can you imagine picking an x that would give you 2 or 3 different y's? No. Every x I pick, say 100, 2 times 100 is 200, plus 3 is 203. Every x I pick gives me only one y. All right, a second thing you're going to be asked, and it's going to be pretty obvious with expressions like this, is what's the domain? What's the domain of a mapping? Why, it's this stuff right here. What's the domain of ordered pairs? Why, it's all the first elements. But what's the domain? What's the domain of an equation? What can x be? And once again, my inclination is that first of all to say, hey, x can be anything. I can pick pi over 7 for x. I can pick 33 1/3 for x. I can pick -1,000,002 for x. Why can't I pick something for x? Which raises a good question. And here's 2 reasons why you can't have a particular x. 2 what I call limitations on the domain of a function. First of all, no value is allowed in the domain that causes the denominator to be 0. Let's say you have this function, f of x equals 3x over 2x minus 8. And here's a question for you. Can I pick anything for x? Yeah, I guess. Oh, wait a minute. Seems I remember something from my earlier days in mathematics, that I cannot have a 0 in the denominator. You remember that? If you have any doubt about that, try to evaluate something like 7 over 0. Your calculator will say error. And I'm reminded I cannot have a 0 in the denominator. All right? With that in mind, is there anything that would make the denominator 0? Is there any x that would make the denominator 0? Some of you can look at it and say, yeah, I see what it is. Something will make that denominator 0, and I know what it is. Others of you are suspicious but wonder what would make the denominator 0. That's why I've given you this strategy. This allows you to find out what makes the denominator 0. Here's the strategy. Set the denominator equal to 0 and solve. Just the denominator. Set the denominator equal to 0 and solve. That means get x by itself. Add 8. 2x is 8. Divide by 2. X is 4. And keep reading. When you solve the equation, you have just discovered what x cannot be. This is the one value in the universe that x cannot be. Why can't it be that? Because it makes the denominator 0. Your domain then is everything except 4. Domain in this case, all real numbers except 4. So my domain when we're talking about a fraction, if there's a limitation, it's going to be expressed as all real numbers except something. The one something that makes the denominator 0. Look at another example. I don't have to use f of x. I can use g of x. Here's a function. Let's say here's a function. G of x equal x over 3x plus 15. And I'm asked, hey, what can x be? What's the domain? As soon as you're asked about the domain, you go to your worksheet and ask yourself these two questions. First question, will any value of x result in a 0 denominator? By the way, I put that as a question at the end. Will any value of x result in a 0 denominator? I'm not sure. If you're not sure, go to your strategy. It tells you what to do. Set your denominator equal to 0 and solve. Minus 15 to both sides. 3x is negative 15. Divide both sides by 3. X is negative 5. Don't forget what you have found when you solve this equation. That's what x cannot be. That's the one value that x cannot be. So my domain is all real numbers, anything in the universe, except negative 5. All right? So if you have a fraction, and by the way, this first one just applies to fractions because you got to have a denominator, right? Can't have a denominator unless you get yourself a fraction. So if you got a fraction, ask yourself the question, will any value of x result in a 0 denominator? Check your strategy to find out. Hey, there's a second question I need to ask myself. And that is, will any value of x result in a negative number under a radical with an even index? Radical being a square root, right? Here's the second limitation. No value is allowed in the domain that results in a negative number under a radical with an even index, like a square root. Square root is where you're typically going to see this expressed. So here's an expression. Let's say you got a function. G of x is the square root of 3x minus 15. And here's a question for you. Will any x cause there to be a negative under a square root? Well, yeah, like 0. 3 times 0 is 0. 0 minus 15 is negative 15. Square root of negative 15, your calculator is going to say error. Square root of a negative, there are no real numbers to answer those questions. So I cannot have a negative under a square root and expect to get a real number answer. How about 2? 3 times 2 is 6. 6 minus 15, there's another one, negative 9. Square root of negative 9, big problem. So there are a bunch of numbers that will make negatives under this radical. How do I find out what my domain is? Strategy number 2. Take the radicand, that's whatever's under the radical, and set it greater than or equal to 0. And solve. Now we're going to get into solving inequalities more specifically, but you know enough to solve this guy, right? Add 15. Solve it just like an equation. 3x is greater than or equal to 15. Divide both sides by 3. X is greater than or equal to 5. Solve the inequality. That's your domain. Once you solve it, you have expressed your domain. So your acceptable values for x are anything greater than or equal to 5. Now, one thing you're going to find out that Hawks asks you is express this in interval notation. Best way to do interval notation is to look at a graph of it first and then write the interval notation based on your graph. So let's graph everything greater than or equal to 5. Here's 5. Greater than 5 is this way. Question: do I put a parentheses or a bracket here at my ending marker 5? Well, because of the equal to sign, 5 is part of my graph, so I'm going to put a bracket. So there's my number line representation of my domain, which allows me to do the interval notation very easily. Bracket at 5 all the way to infinity. And infinity, remember, always gets parentheses. So there's your domain in the way that Hawks is going to ask you to express it. So once again, whenever you are asked about a domain, immediately go to these two questions. And let me give you one more example and let's ask about it. Let's apply these two questions to it. F of x equal 3x squared plus 7x minus 9,281. Oh my gosh. I'm wondering about what the domain is. Anytime I'm asked about the domain, go to these two questions. Question number 1. Will any value of x result in a 0 denominator? Question number 1. No. I'm never going to get a 0 denominator because there's no fraction. There's no denominator. Don't make life more difficult than it is. If there's not a denominator, don't worry about limitation number 1. Will any value of x result in a 0 denominator? No, there's no denominator, so I get a no. Question number 2. Will any value of x result in a negative number under a radical with an even index, like a square root? No, there's no radical. Since there's no radical, there's no way I can have a negative under a radical. I get 2 no answers. If you answer no to both questions, your domain is all real numbers. So my domain, all real numbers. In fact, anytime you have a polynomial, the domain will be all real numbers. Why? Because there's no denominator and there's no radical. So if there's no denominator and no radical, there's no problem. Your domain, all real numbers. All right, let's look at a couple of your Hawks problems, and then I will here's a relation. Here's a relation in x and y. And they ask me, number 1, to write this as a function. Remember how a function looks like? It looks like this, f of x. But let me remind you another way you can write the same concept. F of x is the same as y. So anytime I want to write something in function notation, write something as a function, just solve it for y. All right, so let's get all my y's on one side. So I get negative 6x plus 6 equals, plus x equals negative 6y minus 5y. Like terms. It's negative 6x squared plus x. All right, I'm almost there. So I'm going to divide both sides by negative 11. And I get y is, this looks like a whole bunch of negatives, so I'm going to change every sign. A negative over negative is a positive. Positive over negative is a negative. So I get 6x squared minus x over 11. If you wrote it this way, it would be fine, but it's a little clumsy. So here's my y equals, and if they ask me to write it as a function, I write it as f of x equals 6x squared minus x over 11. So that's the first step they asked me to do, is write this as a function. Second thing they asked me to do is evaluate this function at x equals -3. So what that tells me to do is everywhere there's an x, I'm going to put a -3. So f of -3 equals 6 times, put in parentheses, -3 squared minus -3. Everywhere there's an x, I'm putting -3 all over 11. All right, do my powers first. -3 squared is +9. Minus a -3 is +3 all over 11. 6 times 9, 54, +3 over 11. I get 57 over 11. So f of -3 is 57 over 11. Again, evaluate at a particular value. Everywhere you have an x, 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 you put -3 and evaluate. All right, the third thing they're going to ask me is, what's the domain of my function? Here's my function, f of x equal 6x squared minus x over 11. Now, as soon as they ask me about domain, I go to my 2 questions, which I misplaced. Here they are, my 2 questions. First of all, will any value of x, can you pick a value for x that would result in a 0 denominator? Hey, I got a denominator, so I need to look closely at this. Pick anything for x. Will it ever result in a 0 denominator? No, it won't. Here's why. My denominator is always going to be 0. I will never get anything but 11 in my denominator. It will never be 0. Whatever you pick for x, your denominator will always be 11. So you will never get a 0 in that denominator. So question number 1, no. Question number 2, will any value of x result in a negative under a radical? I don't have a radical, so I get no for that one too. But again, this is a good example to show you that just because you have a fraction doesn't mean you're going to have a limitation to your domain for number 1. So I got 2 no answers. My domain is all real numbers. Now, Hawks wants you to write this in interval notation. How do you write all real numbers in interval notation? Well, think about the number line. If everything is covered on the number line, and that's another way to say all real numbers, every single point is covered, part of your solution set. How do you do this in interval? Well, it's everything from -infinity all the way to +infinity. This is how you say all real numbers in interval notation. All right, good luck on relations and functions.